Equilibrium. So now we get to talk about this particular topic that I introduced but didn't really give you a proper introduction to back in the kinetics chapter. So as you may recall from the kinetics discussion, when looking at a reaction, we do have reactants that in order to turn into products need to go through an activation any energy barrier, which is determined by the energy difference between the reactants all the way to the top of this hill. And that tells you how fast or slow the reaction is going to take in terms of its rate. But when we look at the energy difference between the products and the reactants, the energy difference tells us uh, the overall stability of the products in respect to the reactants. And so the difference in energy from products to reactants or vice versa is what we refer to as thermodynamics. And by now you know that the difference in energy between the reactants going up to the top of the energy hill is the kinetics. So equilibrium, unlike kinetics, does um, basically focus on the thermodynamics aspect of the reaction, and it tells you whether the reaction is likely to occur, and even then it tells you to what extent the reaction may be willing to occur. So looking at this hypothetical case where you have big A, big B, big C, and big D, which are standing and represent molecules, and their balancing coefficients being little a, little b, little c, and little d, you have the process of a reaction that can actually go forward, but then you also have the condition that the reaction can go backwards, and both of those things have their own equilibrium constants associated with it. Now, if we treat this as an elementary step, we can write the rate forward and the rate backwards. And the idea right here is that if you're in a state of equilibrium, the rate going forward is going to equal the rate going backwards, meaning that when you look at this particular reaction, to you it will look like there is no more change happening because the rate at which products are being formed is equal to the rate at which products are turning back into reactants. So basically the process um, cancels out in terms of what you see happening, even though there's a constant reaction, going forward and a constant reaction going backwards. By writing the rate law for both these processes, we have negative K1 times the concentration of A to the little a power times the concentration of B to the little b power. And for the reverse rate or the backwards rate, we have negative K negative 1 times the concentration of C raised to the little c power times the concentration of D raised to the little d power. So pretty much what I'm going to do is I'm going to bring the concentration terms to the same side. Specifically, I'm going to divide both sides by the concentration of A to little a and B to little b from both sides, ending up with this particular expression. Products raised to their coefficients divided by reactants raised to their coefficients. And I'm also dividing both sides by negative K negative 1, yielding the following expression on the left side. And the rate constants divided by each other is what we actually refer to as the equilibrium constant, and we express that as big K with a C as a subscript. So this is the expression of equilibrium, and granted this is based on the elementary steps, but it turns out that this applies to overall reactions much the same way. You can just input the concentrations of the products raised to their coefficients in the overall reaction divided by the concentration of the reactants raised to their balancing coefficients. So we're going to basically do a few examples that depict that particular process, and we're also going to define an extra set of rules as well to make sense of this. Now, first of all, as written, the equilibrium expression, products over reactants, this applies for things that you can actually determine the concentration for the species in question, right? And in fact, the C subscript right here for the equilibrium constant stands for concentration. So we're basically going to be dealing with molarities for each one of the products and reactants for this to be the Kc equilibrium constant. Um, One thing that you're going to find out is that if the value of the equilibrium constant is less than 1, it will never be negative, but if it is less than 1, what that's going to tell you is that you're going to have a lot more reactants than you do have products, right? Meaning that you end up with a number that is less than 1 as a result of having a bigger denominator than a numerator. This is going to tell you that the reaction that you're looking at is reactant favor. You're going to have more reactants than you do have products. If the value of K equals 1, what it will tell you is that you have equal amounts of, well, maybe not necessarily equal amounts, but you're going to have equal values for the product of the concentrations of C and D raised to their coefficients as you would have the concentrations of A and B raised to their coefficients, right? Those two values will be equal. And the other case where K is greater than 1, that will tell you that you have a higher amount of products than you do have reactants, meaning that your fraction is going to be greater than 1 in value. So that will tell you this is product favor by default. So looking at the value of the equilibrium constant will be a means by which you can tell to what extent the reaction is likely to happen, with greater values than 1 for K implying that the reaction is product favor, and values less than 1 implying that the reaction is reactant favor. All right, now let's take a look at the physical states of the reactants and products. Because as I was implying before, the expression right here counts so long as you can determine the concentration of a species, specifically if you can change the concentration of that species. So if you think about this, species that have the AQ symbol, those are species that you can easily dissolve in water, and as a result you can actually change their concentration, to some extent, right? You could make the concentration kind of small, or you could make the concentration rather large, but the point is that you could change the concentration, so it becomes a variable in the expression. And the same thing goes for gases. You could actually dissolve gases in water. So the idea right here is that as long as the substance is a Q or a gas, you can input it into the equilibrium expression. But if you do have a solid, so for instance, let's say you have lead-2 iodide, which is rather insoluble in water. You can see actually the yellow crystals that were produced in this particular reaction where lead was mixed with iodide. What you basically see is that the concentration of the lead iodide, which to some extent actually goes into lead-2 plus AQ and iodide AQ, that particular concentration is not only very small, but it's a constant. It doesn't really change. And it doesn't matter how much of the solid you have present in here, the concentration of lead and iodide remains the same, irrespective of that amount. So as a result of there being no change in concentration, we don't actually input either reactants or products that happen to be solids into the equilibrium expression. And the same thing goes for substances that have the liquid sign. If they have the liquid sign as opposed to the AQ sign, it's being implied that the substance is perhaps in a different phase that's not actually mixing with water. And water itself, you typically write it as a liquid, at least at room temperature. And so water will also not make it into the expression for the equilibrium constants. So just be sure to revisit your solubility chart and remember that in terms of substances, water, pure mercury, pure bromine, those things are liquids, right? So you wouldn't actually input them into the equilibrium expression. Right, and so here you can see an example of that. You have oil or a substance that is a little bit oily in characteristic versus water, and most of it, remains separated. All right, so let's take a look at a few examples that depict this, right? So we're going to only input in here things that are liquids, things that are AQ or gases. All right, now water. One more thing I want to say about water, just to give you an idea. If you think about the quantity, 1 liter quantity of water, and the fact that the density, as just to easy the approximation, we have a density of 1 gram per ml for water and a molar weight of 18.02. So what that basically tells us is that the 1 liter of water, if we convert that to mLs, and then use the density to change the mLs to grams, and moreover use the molar mass of water to change the grams to moles, you're going to find out that the 1 liter of water is equal to 55.5 moles of water. And even though it's not exactly correct to say, but because those 55.5 moles of water are present in 1 liter of water, technically speaking, the quote-unquote concentration of water will be 55.5 molar, which needless to say, this is huge. This is humongous. This type of concentration is larger than most of the highly concentrated substances that you could actually make. If you think about concentrated sulfuric acid, which is actually rather corrosive and dangerous, especially if you get it on your skin, that we're talking at most about a concentration of like 18 molar, right? And that's, really highly concentrated sulfuric acid. So the fact that water is this concentrated, 55.5 molar, means that its concentration is not going to change all that much, even if it's actually a reactant or product in the reaction. You'll change a tiny bit, but that tiny bit is going to be kind of inconsequential in terms of the 55.5 molar, amount that you have to start with. All right, so let's do a few examples just to give you an idea. If we have the following equation, everything here is a gas, so everything will make it into the expression. All you do is you simply say, okay, you have Br2 as a product, you have Cl2 as a product, the balancing coefficients are 1 and 1 for both of them. And for the reactant, you have BrCl, which is the reactant, and the coefficient is 2. So when you write the equilibrium expression, you have concentration of Br times concentration of Cl2, all divided by the concentration of BrCl raised to the second power. And the reason we're including Br2 in this expression is because it's currently present as a gas in this particular expression. And for that to happen, that means that the temperature has to be, slightly higher than room temperature, for you to actually have Br in the gas phase. All right, now let's take a look at another one. We have magnesium oxide solid reacting with carbon monoxide gas, yielding magnesium solid and carbon dioxide gas. This is an actual reaction that you can enact in a proper furnace to isolate the pure metal from its ore. But basically, the equilibrium expression is simply going to be the concentration of CO2 divided by the concentration of CO, because MgO and Mg, they're both solids, and as such, they don't make it into the expression itself. All right, as a second example, let's take a look at the reactivity of weak acid, hydrofluoric acid, turning into hydronium and fluoride. We're going to investigate this type of reaction more in detail in further in a lecture that is yet to come. But the idea right here is that as far as products, H3O plus, known as hydronium, and fluoride both make it into the expression. They're both raised to the first power since those are their balancing coefficients. But for the reactants, only HF gets to make it into the expression since it's the only species that it's AQ or gas. Alright, and one more example. We have a titanium solid reacting with 2 equivalents of chlorine gas. And you form titanium chloride, titanium 4 chloride as a liquid. Because the only thing here present as a liquid, as a gas or AQ is Cl2, that means that the products, you don't have anything that can make it into the expression. So the only thing you could put for the products is just 1. But for the reactants, you'll have the Cl2 concentration raised to the second power. Alright, I'm going to look at some of the balancing coefficients before I end this video. And then I'll give you an example in the next video. But the balancing coefficients do affect the value of the equilibrium constant. So what that means is that if you change the reaction, so right here we have the 2 BrCls forming the Br2 and the Cl2, right? And we already got the expression in the previous example. But if you were to actually change the balancing coefficients, namely multiply everything by 1/2, this is still balanced as a reaction. But what ends up happening is that the equilibrium constant now is changed. Instead of having the concentration of Br2 times the concentration of Cl2, you have the concentration of Br2 raised to the 1/2 power, the concentration of Cl2 raised to the 1/2 power, and everything is divided by BrCl. And what this shows you is that the new equilibrium constant expression is actually equal to the regular equilibrium expression that we had at the beginning, except that that whole thing is now raised to the 1/2 power. In other words, we're taking the square root of the original equilibrium constant. So the point right here is that whatever coefficient you end up multiplying the entire equation by ultimately becomes the exponent that you apply to the equilibrium constant. And that's how you can change and recalibrate the value of the equilibrium constant. So multiply by a number, multiply the equation by a number, raise the equilibrium constant by that number. Okay, so that's one of the things to keep in mind. The other thing is that if you, let's say, reverse the equation, right? So now the products are on the reactant side and the reactant is on the product side. All that happens is that now the BRCL raised to the second powers of the product, and so it's on the numerator of the fraction. So what ends up happening is that you basically end up dividing what you had before from 1. You basically take the inverse of what you had before, right? So if you look at the original expression for the equilibrium constant, BR times CL2 divided by BRCL squared, you're basically taking the inverse of this, or you're raising it to the -1 power in order to get a new expression. So long story short, if you do reverse the reaction, right, if you actually turn the products into reactants and reactants into products, you have to raise the equilibrium constant to the -1 power. So that's the other thing that happens here, right? So multiply by a constant, which in this case the constant is -1, you're raising the equilibrium constant by -1. All right, and I'm going to show you an example in the next video. So this is everything I want to tell you in terms of the little definitions and the little rules that we have to use for depicting the equilibrium constant. So in the next video, I'll show you an example and we'll dig a little bit deeper.